All right, good morning. So, week 3. Hope everybody had a decent weekend. Um, and lots of stuff I want to talk about today, starting with Lab 2, which I think there's a lot of conversation about already. Um, and I want to talk about Lab 2. I want to talk about homework 2. We're going to go through how to go from truth tables to equations, and then from equations to circuit diagrams, a few different ways, including doing a product of sums as opposed to a sum of products. We'll talk about what that is, and we'll be talking about product of sums for the next couple of weeks. We'll talk about something called K-maps for simplifying equations, um, which will be a good topic because it means the circuits that you're going to end up building will be less complex in many cases than the circuits that you sketched out in Lab 2. So we'll learn how to reduce the number of gates and the complexity of the wiring in very systematic ways. And that should give you everything you need for homework 2. Remember, homework 2 has been pushed back. Um, and then we'll talk about Lab 3, um, which will be due. I don't remember when I posted it, but it's not the usual due date. There's some extra time in there. Um, so let me start off by talking about Lab 2. And let me pull up my notes. And what I'd like to do is just go through Lab 2 with you and talk about two things in parallel. One, what you should be doing in these labs as far as write-ups and such, but then two, also looking at the particular experiments and seeing, what you might have expected as far as observations and results and so on, because a lot of people got different behaviors from their circuits and so on. So um, to some degree, that's okay, right? When you're doing an experiment, perhaps an experiment that hasn't been done by many people, you don't know what you're going to get. You may think something's going to happen, but what actually happens could be very different. And that's kind of the exciting part of science, right? Is when you find something new, there's something unexpected going on. This is where breakthroughs occur in science. But for the most part, the experiments you're doing in the labs for this course and for 270 should have pretty predictable results. So I want to look at kind of what should be happening and discuss some of the things that could cause differences. So let's just start with Lab 2. So LED usage. So first thing to note, and I think everybody was okay with this for the most part, LEDs are directional, right? So plain old light bulbs like you buy, at Radio Shack when Radio Shack was around, you could hook them up either way that you wanted. There's not a positive and a negative side. You're just running current through a filament. LEDs are directional. You have to put a higher voltage on this positive side, which is called the anode, and a smaller voltage on this negative side, or cathode. And so your current flows in the direction of this triangle. And if I put 5 volts over here and ground over here, the LED should light up. If I put too much current through, more than say 30 milliamps, the LED may fail. But if I put 5 volts on the left and ground on the right, the LED should not light up. So this is a version of a device called a diode. A diode is like a one-way valve. It lets current flow in one direction but not the other. So if I put a high voltage on the left, the diode part of this device does not let the current flow through, and so the light emitting part does not light up because there's no current. So you see a typical circuit like this, and the high voltage is on the left over here, so it's on the anode. The low voltage is on the right on the cathode, and we've got the 1K resistor to reduce the amount of current. So if this is a 5 volt drop, and we have 1 kilo ohm, then that's about 5 milliamps, which is a normal amount of voltage of current to run through your LED. So we had 3 configurations here. The first configuration looks very much like this. The resistor can go on either side. When you're thinking about LEDs, hold on, I got a problem here. When you're thinking about LEDs, they kind of work like this. Alright, so this is an LED. The current will flow in this direction. And we usually think of these as not having a voltage drop and not having resistance. And if we go back for a minute to 120, remember when you have a resistor, let's say you have 5 volts, and you have some kind of resistor in here, if we think of this as ground, so voltages are always relative, right? There's no such thing as just pure 5 volts. It's always 5 volts higher than something else. So anytime we analyze a circuit, we're taking voltage readings relative to ground. So if this point of our circuit is at 0 volts, everything along here is 0 volts. Wires don't change voltage. So all of this is 0. And if this is 5 volts coming out of the top of the battery, everything along here is 5 volts. Wires don't change voltage. Which means we've got 5 volts here and we've got 0 volts here. And how is that possible that this point in our circuit is 5 volts and this is 0? Because resistors cause voltage to drop. That's what resistors do. And there's a current flowing. Let's call it I, and so there's this magic relationship V equals IR, which relates the voltage across the resistor, the resistance, and the current through the resistor. We don't need to worry about that too much in this course, but if we think about the case of an LED, since there is no resistance, there is no voltage drop. Which means if I were to build this circuit, and instead of having a resistor here, I just put an LED in. Well, I have 5 volts on this side, 0 volts on this side, but this is basically a wire. It's a short. There's nothing in here that reduces the flow of current. There's nothing in here that should drop the voltage. And so if we calculate the current, we have 5 volts equals your current times 0. Your current is effectively infinite. And that's what causes the LED to fail. So when we build a circuit like this with 5 volts, a resistor, a diode, and ground, or like the typical circuit with the resistor on the left, the only thing the resistor is doing is cutting current flow. So if I put a resistor over here and I put 5 volts and I put ground, well, since this is 0 volts here, and the diode does not cause a voltage drop, this is 0 volts here. And we can analyze this part of the circuit exactly like we did in 120. We can say there's a current here. There's a voltage drop of 5 volts. There's a resistance of 1 kilo ohm. This is going to be 5 milliamps. Just 5 divided by 1,000. And since this is in series, the current going through here is also going to be 5 milliamps. Oh, I messed that up. Yeah, I messed that up. Hold on. Oh, let's see. How do I do this without getting too deep back into 120? There's no voltage drop across the diode, so this is 0 volts here. But think of this as a box that has 1 kilo ohm resistance and a 5 volt drop. So we have 0 volts on this side, 5 volts on this side. And so just think of your current flowing through this. And that voltage drop is equal to the current that we don't know times the resistance. Well, this has no resistance. This is 1K. Resistors in series, this is 1,000. So there's your current of 5 milliamps. All right, so first configuration, you end up with 5 milliamps flowing through the diode in this direction. That should make it turn on. And I think most people, that's what they observed, was in this first configuration, the LED lit up. All right, the second configuration is different because we have an inverter. We have the left side labeled low. We have an LED. We have a 1K resistor. And we have ground. All right, this is ground over here. So this is 0 volts. And so the question is, what is the voltage at the input of this? And if this is 0 volts, then you've got 0 volts here, 0 volts here. There's no current flow. But this is an inverter. We said the L is 0 volts. It's logic 0. And if you put 0 volts into an inverter, what do you get out of the inverter? What's the output? You get logic 1. So what voltage is coming out if that's a logic 1?
5 volts. Okay.
It's approximately 5 volts. So this looks almost exactly like the first configuration. We have 5 volts over here. We have an LED, we have a resistor. Well, that's this typical configuration. 5 volts, LED, resistor, and ground. So this should be a configuration where the LED lights up. The only differences are, one, this voltage will actually be a little less than 5 volts. Now in tinkercad it may be 5 volts. But in a physical protoboard with a physical chip, this might be, 4.5 volts. Because these devices don't put out exactly the full 5 volts that they should in theory. The other thing is the amount of current coming out of here could be limited. Now we only need 5 milliamps to make this LED light up. But in some types of logic chips, this thing might only put out 4 milliamps. And so you should see this light up, but it may not be as bright. And I don't think we can observe that in tinkercad, but again, with a physical protoboard and components, you might see a difference in intensity. All right, and then configuration 3 is perhaps a more interesting one. So we have a high input going into an inverter. And then we have what looks like a backwards LED, a 1K resistor, and then VCC, or 5 volts. Alright, if this is an inverter and we're putting in a highest 5 volts, what do we expect the output of that inverter to be? What logic level or voltage level? Yeah, 0 volts. So this voltage right here is basically ground potential. And so this whole circuit should act something like this. And that's just our typical configuration, drawn mirror image left to right. 5 volts goes through a resistor, goes to the LED, goes to ground. That should also light up. And so all three of these configurations, your LED should light. So if you had a configuration where it didn't light, I suggest go back and take a look at your circuit again and see if you can figure out what's going on. In this third configuration in particular, one thing that sometimes happens is people get the LED hooked up backwards. And it's pretty easy to do. The directionality is almost the same unless you look for the little bend in one of the pins, or you hover over those pins in tinkercad and wait for the pop-up to say, you know, anode or cathode. So go back and redo your circuits sometime and make sure you can get all three configurations to light up. All right, let's talk about the write-up for experiment 1. Again, your goal is to produce a report that you could hand to somebody and they could reproduce your work and either confirm your observations or, you know, observe something different and then, you know, refine the theory to take into account whatever was missing from the original theory. So you want to, you know, say in experiment 1, we're working with LEDs, resistors, and logic chips, and seeing under what conditions LEDs turn on or off, or something like that, right? So how do you do that? Well, you construct 3 circuits. What are the 3 circuits you constructed? So again, a tinkercad screenshot makes, you know, a nice sort of visual way to share your observations, but that's not sufficient to let somebody reproduce your work, right? They would have to know what tinkercad is, they'd have to know what these pins are, they have to be able to follow your wires, and then from that produce these diagrams, right? You want these diagrams in your lab report. Anytime you build a circuit, you got to tell the person what circuit you built. Anytime you talk about, you know, observing the output of an LED, they better know exactly what that LED is, how it's hooked up, what it's hooked up to, what you did to it when you were testing the circuit. Easiest way to do that, just put these diagrams in, or draw them yourself, or whatever diagram corresponds to the circuit that you're building, but you got to have a circuit diagram in there. Now, for experiment 1, you don't need to put in part numbers, pin numbers, component ID block, etc., right? All you're trying to do is what this experiment asks, which is set up these configurations, record your observations. But your observations don't mean a lot to the reader unless they know what these configurations are. So you got to have these things in your lab report somewhere. So that's the first detail. The second detail, if you copy and paste this and put it into your lab, you've got to put a citation on it. And almost nobody did that in lab 2. And that will potentially get you kicked out of college in the future. I mean, not from this course, but at a university or on a job. If you publish a report with information in it that is not your own and you don't cite it, it's considered plagiarism. And it can get you in a boatload of trouble really, really quickly. So I'm going to start taking off points for this with lab 3. If you take anything and put it in your lab report and it's not your own words, if it's not your own picture, if it's not your own drawing, that is totally fine as long as you cite it. So cite any material that's not your own. How do you do that? Let's say you copy this. Let's say your lab report says, okay, first we built the following configuration, and then you put in a copy of this picture right here, this upper part. Just put a little, you know, sentence below it, taken from ENGR250 Lab 2, page 7, right? And you're covered. Then we built a second configuration as shown below, put in a picture of this, put the same note on there. And don't just, you know, put a note in the front saying any pictures that aren't mine came from Engineering 250 Lab 2, right? Cite each source. And ideally, you're drawing these by hand, right? It will help you think about the circuit you're working with if you're actually drawing it out instead of copying and pasting. But, you know, more complex circuits like down here, you're welcome to copy and paste those. But make sure you cite them. All right, so any questions on experiment 1? It's a fairly kind of might feel like busy work sort of experiment, but it can be really useful. And this third configuration in particular, this will come back in your traffic light experiments in ways that'll help you reduce the component counts that you end up with. The idea that a low voltage right here causes the LED to turn on, that's something to keep in mind. All right, let me just talk about wiring the inverter, and let's just go into Tinkercad actually. So let's just play around with this third configuration. It's a good one to pick on. So let's put a protoboard in here. And let's get a power supply. And let's get a chip. And a resistor. And an LED. All right, so you know that on this protoboard all these holes on top are connected to each other. All these holes on bottom are connected to each other. There's no connection from the top to the bottom. And then we have these horizontal rows where everything is connected together. So the first thing is, you know, where are you going to put this chip in your board? And if you put it somewhere like this, there's a really subtle but significant problem. The problem is everything in this column 10 is connected together, right? All 5 of these holes, which means this pin, which is called ground, and this pin, which is called output 4, are shorted together. And this pin, which is output 3, and this pin, which is input 4, are shorted together. And so if you put this chip right here, you're connecting pins to each other that you didn't necessarily intend to connect. And if I put it down here, exactly the same thing happens. And there's only one way you can put this chip on this board where that doesn't happen, and that's to go across this middle section. So if I put this, say, right here, I've got 5 connection points for this bottom pin, which is called ground. I've got 5 connection points for this upper pin, which is output 4, but they're not shorted to each other. So now if I want to connect to output 4, I can use any of these 4 holes. If I want to connect to input 1, I can use any of these 4 holes, and so on. So that's the first challenge, is putting this in the correct place. All right, let's hook up power. So I'm going to use ground. And come across like that. And I'm going to put power. And I'll stick with red for power. Come across like that. And then I'm going to make power available on both the top and the bottom of the protoboard. Like that. And then I'll do the same thing for ground. Alright, so this is always a nice way to start your circuit wiring. Give yourself access to power. All your chips are going to need power. A lot of the other parts of your circuit will need power. So this gives me 5 volts all along here, 0 volts along here, and along here. Alright, next thing is the 7404. So pull up the data sheet for that. And eventually these data sheets start to look all the same. And just about the time that they look the same, we'll throw a different one at you. But for now, 7404 looks like this picture right here. Pin 7 is labeled ground, 14 is VCC. These are not inputs to inverters. This is how you make the chip work. This is how you plug it into the wall. Pin 7's always got to go to ground, 14's got to go to VCC, which is 5 volts for us. So we're going to come over here and we're going to take pin 7 and just make a connection straight down here to ground. And then pin 14, we're going to go ahead and connect to VCC. And the colors of these wires don't make any difference. But when you're doing this with a physical protoboard, if you mess up power and ground, if you accidentally connect this to ground and this to power, your chip gets really hot, it smells bad. If you touch it, you burn your finger, and then the chip doesn't work anymore. So if you build a protoboard with 50 chips on it, and just one of them is backwards, that chip will fry, but it might also take down other components with it. So getting the plus and minus, the polarity of your wiring right, is really, really important. And increasingly difficult as your circuit gets more complex. So a lot of times people will color code their wiring, and when you do this with physical parts in the lab, there's colored wires in your parts box, and you can use those to help keep track of plus and minus. All right, so this is a what I would call a properly wired 7404, properly powered. Nothing weird happens when you use it. It takes some current, right? It's not doing anything, but it's an electric device. It takes some current to operate. 17 microamps. Well, that's not a lot, but it's something. All right, so let's build configuration 3. We want the input to be high, logic level 1, and I'm just going to use pin 1 and pin 2 as my input 1, output 1. All right, I'm going to use green wires here just because they're not power connections. So pin 1, I'm going to connect to 5 volts. Now this may make tinkercad unhappy, but that's okay for now. The output of the inverter comes on pin 2, and that should go into the negative end, the cathode of an LED. And so here's another place that you can have difficulties. If you try to put your LED right here, well, I've got the negative side connected to input 2, that's great. But look at what's happening to the positive side. It's in the same column as pin 3. Right, so I've connected input 2 to the anode of my LED. And that's not part of this circuit. I should only have a single inverter, which is input 1, output 1. These chips are a little tricky to work with because they take up 7 sets of columns here and 7 sets of columns here, and you're not allowed to do anything with these columns unless you're trying to connect to one of these 14 pins. So even though I want pin 2 connected to the anode, the cathode of my LED, I can't just put my LED right here. I got to use a wire. So I'll take a wire from there and I'll just plug it into any hole in this column. And now pin 2, which is the output of my inverter, is connected to the cathode or negative end of my LED. So I've got my high, I've got my inverter, I've got this wire right here. Here's my LED. I need the positive end, the anode, to go through a resistor. Well, in this case, I can just take my resistor and put it right here. And now the anode will connect to one end of the resistor, the other end of the resistor connects to 5 volts. But I don't have to do that. I could rotate my resistor and do this and make this look like my circuit diagram. So now I have high coming in here, here's my inverter, there's the output. That goes through a wire into the negative side of my LED, that's right here. Here's the positive side of my LED right here. That goes through a resistor right here, and then this end over here goes to VCC. So I can put another wire over here and maybe run that up to VCC. And so there's a setup for my circuit. So if I run that, my LED turns on. One comment about input current. Normally, when you have an input to something like an inverter or a logic gate, it would be wrong to just connect this directly to 5 volts. In some versions of this chip, that would cause a little explosion symbol to appear in the middle here. But a 74HC04, you can connect these inputs directly to 5 volts, and it doesn't flood it with current. The datasheet tells you these kinds of details. But if Tinkercad's happy, you're good to go. So when wiring your circuits, a lot of times I find it easier if I try to make the physical layout match the way the things are laid out in my circuit diagram. And you know, I can rewrite my circuit diagram pretty easily compared to rewiring my board. So if I don't think this is going to be a layout that I want to use, I can change this around, right? I could draw my LED going up and down, or I could put my inverter on the right side, or you know, whatever makes sense to me. All right, so any other questions on experiment 1?
Could you run through drawing a schematic again?
Yeah, let's do that when we get to experiment 6, because that's the one where it came up mostly. And for experiment 1, I just need to know, you know, what did you connect? So using logic symbols is fine for that. All right, experiment 2. Same idea, right? You've got to tell the person what your circuit was that you were building and observing. So your goal is to build this circuit using this switch block, and you know, pick one of these switches to represent this switch. And so here again, this is an inverter, this is an inverter. If we think about what this will do, if the switch is open, or if the switch is closed, let's make a truth table. So let's start off with the switch being closed, which means this side of the switch and this side are connected together, which means this point right here, this junction, is at 0 volts. This is ground, This is basically a wire. This is ground. 0 volts going into an inverter. This is 1 volt coming out here at this junction. And we've seen this configuration before. An inverter with 0 volts going in, this LED should light up because this output of the inverter is 5 volts. So you've got 5 volts at this junction going through an LED 1K resistor to ground. L2 should light up. So L2 should be on. So this is expected. On the other hand, since this is ground, logic 0, this is logic 1 here, we have a high logic right here going into an inverter. The output of the inverter is low, which is ground. Here's the cathode of an LED, here's the anode 1K to 5 volts. This is configuration 3. This is an inverter with a logic high going into it, the output connected to the point of the LED, the other end of the LED going to VCC. That's exactly what we have here. VCC 1K, LED in this direction, logic high coming here. And why is it logic high? Because we have a 0 here and the output of the inverter is high. So we have high going into the inverter. Right, that's configuration 3. So high goes in here, L1 should turn on also. So this will be on. If the switch is open, there's no connection between this point and ground. So this lower part of the circuit we can just ignore. Has no effect. So we have 5 volts up here going into an inverter. We have a low voltage coming out. So this is going to be ground on this side. This is going to be ground on this side. There's no current flow across L2. L2 should be off. And since this is high coming into the inverter, low here, going into this inverter, this is high or 5 volts over here. So this end of the LED is 5 volts, that end of the LED is 5 volts. There's no current flow because there's no voltage difference. So L1 will also be off. So this would be our expected behavior. And we could replace this with 1s and 0s by using this guide here. It says if the switch is closed, that's a 0. So closed is a 0, open is a 1, on is a 1, off is a 0. So this is a great thing to have in your report, right? What do you expect the circuit to do? Because, you know, when you do an experiment, it's usually not just, hey, let's see what happens when I mix these two chemicals together. Usually, you're testing a hypothesis, right? We have some expectation based on experiment 1 and Ohm's law and other stuff that, you know, when this switch is open, these two LEDs will be off and vice versa. So you can describe that, and then you can summarize it with, you know, something like a truth table showing the expected behavior. And then, you know, I built the following circuit, and I put the switch in 2 different positions and recorded the behavior of the LEDs, and here's the observed behavior. And you could put another table in here saying observed behavior, or you could say, you know, the observed behavior was the same as what I expected. But now it's really clear to the reader, hey, what did you do? You built this circuit, right? And you expected a certain thing to happen, and that's exactly what happened. All right, experiments 3 through 5, you were given circuits for these. Build the circuit and observe the output based on the combination of input A and input B. And so bye, have a good day. So input A, right, this is a switch. It's like these switches here. This is the switch we're pretty much going to use for every experiment in this class, and probably every experiment we do in Engineering 270. And the standard way to wire this switch, we have a 1K pull-up resistor, and then we have a switch which can pull down to ground. And if the switch is open, this point will be a logic 1 because it's pulled up to 5 volts, and if the switch is closed, this point will be connected to ground, so it'll be a logic 0. So with this type of wiring, open is going to be 1, closed is going to be 0. And you can confirm that with a multimeter, right? You could take a multimeter, hook one end to ground, and put the other end on input A and see what happens when the switch is open or closed. The slightly odd thing is if you put your switch in this orientation, when you slide this little piece of plastic up to where it says on, that's a logic 0. And you know, light switches in most houses, when you flip them up, the light turns on. We think of that as the direction where things happen, right? So if you want that up position to mean logic 1, just take this block and flip it over 180 degrees on your protoboard so that on is on the bottom. And now in this position where all of these switches were down, the output would be logic 0, and when you flip the switch up, it would be logic 1. But whichever way makes sense to you, that's fine, right? But when you make your truth table, you want to know what the zeros and ones, what the logic values are. So if I'm testing my circuit, and I put both switches in the bottom position where it says off or where it doesn't say on, right? Those are cases where the switches are open. That's logic 1. So if both of these switches are open, I am testing the input configuration 1, 1. So when you write your truth table and you list your 4 combinations, this bottom row is where both switches are off. This top row is where both switches are on. And it's relatively easy to get those swapped. But since this is an AND gate, right, 74HC08, when you come up with your truth table, it should look like the truth table of an AND gate, like that. So in some cases, the 1 was up here and the zeros were down here, where 0 and 0 should not give you 1, and 1 and 1 should not give you 0. So you're expecting a 7408 to be an AND gate, and you build the circuit, and you run these experiments where you go through the different combinations, and you observe the output of the LED, and you record your observations. Now's the time to step back and say, does this make sense? Do my observations back up my hypothesis that this is an AND gate? And if your truth table came out 1, 0, 0, 0, or came out 0, 1, 1, 1, or came out 0, 1, 0, 1, there's a problem. Your circuit observations did not back up your hypothesis. So is there a wiring problem? Is your hypothesis wrong? Did you observe something incorrectly? Right? This is where you go back and you take a step back and say, you know, what exactly should be happening here? Well, let's suppose that you got something like this. I'll put question marks around this so you know this isn't what you should get. Let's suppose you got this behavior, and you come back and you say, wait a minute, that's not an AND gate. All right, let's check our observations. Let's put our switches so that the inputs are 0, 0, and the output we said was a 1. And let's come back to our circuit and take a multimeter and hook the negative end of the multimeter up to ground, and then take the positive end and just put it into whatever hole is connected to pin 1 here. And put your switch in your position where A is 0. And if you measure the voltage, you're going to see 5 volts instead of 0 volts. And right there, that's a huge learning moment. That's saying, hey, you know, I turned switch A on, but I turned switch A off, but the output was 5 volts instead of 0 volts. What's going on, right? So come back to your schematic, come back to your notes, come to office hours, something. Hey, why is it that when I turn the switch off, I get 5 volts coming out? Oh yeah, because it's connected to 5 volts. Well, what happens when I turn it on? Oh, it's connected to ground. I get 0 volts. It's backwards. Aha moment, right? And once you've done that, you probably will never do that again. And when you're working with, you know, lab partners in 270 or other classes, and they're like, I think something's backwards here. You're like, yeah, you wired your switch backwards. You're looking at the zeros and ones the wrong way. That kind of thing, right? And that those aha moments are the most valuable learning experiences you can have in college. Far better than anything I can tell you in lecture, anything you can see on YouTube, anything you can read in the book, right? That's why we're doing labs in this course. That's why the labs are such a big part of this course. Because labs and homework, that's where you're going to learn the stuff, right? Homework's where you're going to learn the theory. Labs are where you're going to learn how the theory relates to the real world. All right, so that's the deal with these next 3 experiments. This is an AND gate, this is an OR gate, and this is an inverter. And so input A is a red herring, right? Input A goes into pin 1. Well, that's the input of an inverter. The output of that matching inverter is pin 2, which doesn't go anywhere. So input A should have no effect on your circuit's behavior. Input B, on the other hand, is the input of an inverter whose output is on pin 4, which is going through an LED. And so your expected behavior on experiment 5 would be something like this. Right? You would expect that the output's going to be the opposite of whatever the input B is. Because input B goes into pin 3, and if you pull up the data sheet, that's the input 2, right? It's the input to the second inverter. And the output of that second inverter goes through an LED, going through a resistor, going to ground. And input A has no effect. But a lot of the observations that people reported showed the opposite behavior here. They showed that the output was the opposite of input A, and that input B had no effect. Well, that does not match the circuit diagram. And if you think about the circuit diagram, input A shouldn't change the output. The only thing input A does is feed the input of this first inverter, and the output of that inverter doesn't go anywhere. So it's basically a red herring. So confirm that this performance is consistent with the 74HC04. That's what we're talking about here. All right, experiment 6. So I went back to the lecture video, and it looked like we spent about 30 minutes on this last week, talking about the requirements for the schematic diagram. And this is exactly like the traffic light experiment from the previous lab, except you're adding a schematic. Right? So you've already got the intersection, you've already got the system diagram, you did the truth table before, now you're adding a schematic. So this is all about drawing the circuit diagram. And so what are the specific pieces of a schematic that you need to make sure you include here? So logic symbols. You know, OR gate, AND gate, inverter, etc. Pin numbers. Right? These gates correspond to pieces of physical chips. And to wire your circuit together, you need to know, well, which of the 14 pins on a 7408 should I connect this particular lead to? So you choose pin numbers, and you say, okay, let's use pin 1 and 2 for these inputs and pin 3 for this output. Part numbers. So you're going to label each gate as coming from a particular physical package. Component ID block, which is this thing in the upper right, which is a part, description, VCC, ground, no connection, and so on. Project ID block, which goes in the lower right, and has your name, has the date, has, a couple of words of description. Traffic control circuit, lab 2, engineering 250. That's fine. Switches and LEDs. This is a wiring diagram. This is something you hand to somebody and they build your circuit for you. So having something like this going into your circuit, well, there's no component called G, right? And you can't take this and change the value of the input by doing something to the letter G, right? So you take your input and you run it through a 1K resistor to 5 volts and you have a switch and this goes to ground. There's an input. Your output has to go through an LED resistor to ground, or maybe a different configuration. Maybe your LED is backwards and the other end's connected to VCC or something, but you've got to have, something in your diagram that says, how do I wire my switches, how do I wire my LEDs, and these have to be labeled. So this might be my green input, and this might be my west input, and this might be my green west output. And the labels you use in your schematic diagram have to match your system diagram, your truth table, and your equations. If my system diagram calls my input car west, and my equations call it W, and my circuit diagram calls it west, I've got three things that I can't relate to each other. Your goal in this whole process is to start with a requirement, right? Design a traffic light controller that does the following, and end up with, ideally a physical circuit that performs the required functions. And so we have this process where we go from some, problem description, we write a system diagram, which is that, high-level view that just shows inputs, outputs, but doesn't show you how the inputs change into the outputs. But it defines what the inputs and outputs are. This is where we notice that we have, for example, 6 outputs instead of 3. Because we're going to have 6 LEDs, 3 red and 3 green. Eventually we're going to have 9. We're going to have 3 yellow outputs. And we have 3 inputs because there's 3 car sensors, 1 per lane. And then using that view of what the inputs, outputs are and what the problem description is, we come up with a truth table that says what should happen in that rectangle in the middle of the system diagram. How should inputs change into outputs? Which outputs do we get for which combination of inputs? And then once we have a truth table, we can write equations. We're going to work on that this week. And then once we have equations, we can simplify those. We're going to work on that this week too. And once we have our simplified equations, oftentimes we'll come up with a logic diagram, something that doesn't have pin numbers or part numbers, but just sort of shows us the logic gates that we're going to use. But eventually we're going to have a complete schematic diagram that has pin numbers, part numbers, switches, LEDs, component ID block, all of that stuff. And then from here we can get to the physical circuit. Or for us right now, tinkercad. And one way to think about this, as far as, do I have the right information? The problem description is what the customer gives you. Hey, I need a traffic light controller, here's what it should do. Alright, you come up with a system diagram and a truth table based on the problem description. Once I've got these things, the rest of this can happen without knowing anything about the problem description. The system diagram and the truth table have enough information to come up with equations. Right? Everything I need to know is in these two pieces. And really, in some sense, all I really need to know is the truth table. When I want to hook it up, I need to know, should I feed in a 1 when there's a car or a 0 when there's a car. But I never need to go back to the problem description. And once I have these and I can come up with equations, once I know the equations for my circuit, I don't need to know any of this stuff. Right? All I know is I need a circuit that, generates these outputs using these equations. And I can simplify those. And once I have those simplified equations, that's all I need to make a circuit diagram. And once I have a circuit diagram, that's all I need to implement it in Tinkercad. I never need to look at any of this stuff again. And so your circuit diagram better have enough information to build your physical circuit in it. So should my output LED turn on or off when the logic output is a 1? I don't know. Normally when the output is a logic 1, we want our LED to turn on. But sometimes you might want to wire things differently. It might take fewer parts if you wire it up so that the LED turns on when the output feeding into it is a logic 0. So you're going to switch your LED around into that third configuration. Well, that's got to be in your circuit diagram. If your circuit diagram just has an output labeled, west red, well, what do I do with that? Do I run it through an LED? Do I need a 1K resistor? Should the LED be facing forward or backward? What should the other end of the LED be connected to? I don't know, because I don't have this information here. I didn't do this part. All I've got is a circuit diagram, and I'm trying to build a Tinkercad circuit or a physical circuit. All the information has to be in there. So you can think of this as kind of like a series of handoffs. And typically, one person might do this, someone else might do this, or a computer might do this, somebody else might do that, somebody else might do that. Alright, so that was experiment 6. And we're going to talk about, coming up with equations from truth tables in more detail and a lot of different ways to do that, and then going from those equations to circuits. And I saw some difficulties with somewhere along that process. People were running into issues, and those are really great points to come by office hours or lab hours, right? If you've got a set of equations and you're not sure how to build a circuit to implement those, right? That's definitely something we should talk about. That's part of this course. If you've got a truth table and you don't know how to come up with equations, that's definitely something we should talk about. That's part of this course. This is a process that you went through in 120, so it shouldn't be completely new, but we're doing it a lot more, right? So in 120 you had maybe a aircraft landing control circuit where you had 3 planes, 3 runways. I don't know if they're still doing that one. But same basic idea, right? Going from a description to a truth table equation circuit. But this is the point of these labs, is to kind of dust off those processes or learn them more deeply, and then be able to apply them. All right, new experiment. So saw some good new experiments, but also about half of the new experiments I saw were simple variations on the experiments in the lab, right? Um, and it says right here, and we said in class, experiments should be related to the material covered in class, but not similar to one of the experiments in the lab. And I got multiple new experiments that said, let's repeat what we did in experiments 3 through 5, but let's use an XOR gate, right? Well, that is a cool experiment, I agree, but it's very similar to the experiments in the lab. So I'm going to up the bar on the new experiment for lab 3 and say, really try to think of something different. Now, I've already said you can't do traffic light new experiments for the rest of the course, and lab 3 is really one experiment, which is the traffic light controller. So both of those will kind of compel you to come up with something different from, you know, a modification of the traffic light experiment. So keep thinking about new experiments. I'm seeing a lot of really cool, clever ideas, so keep working on that. All right, other questions about lab 2? All right, let me talk really briefly about lab 3. And I don't think we need to get into too much, I don't think we need to dwell on this too much. This is all spelled out here. So lab 3 is the traffic light controller. So let me just pull this up. All right, so one experiment, intersection control signal system. So same drill, three-way intersection is in need of a signal, blah, blah, blah. So complete the following sketch. Sketch the intersection, identify the values for ones and zeros, you've done that. System diagram, right, not mentioned in here, but it's mentioned in the details. Truth table, and then using sum of products and logic gates available on tinkercad, come up with a design for a circuit to implement the control system. All right, so I spell out a lot more information about these details in Canvas, so we'll mostly concentrate on that. But basically, you're going to come up with a circuit representation using sum of products, and then you're going to come up with a different circuit to solve the same problem using product of sums, and then you're going to compare your two designs. And then you're going to pick one of those two designs, and based on which design you pick, you're going to minimize it, and then implement and test the design in Tinkercad. A few people already implemented their circuit in Tinkercad for Lab 2, which is great. You're ahead of the game. But this is going to be very specific. All right, it's one experiment, so all 100 points rest on this one experiment. And in Canvas, and I just updated this, 2 minutes before class started, and you should have a note, so make sure you've got the most recent download. Important clarifications to receive full credit. All right, so explain what you're doing. Have an introduction, right? Describe experiment 1, building a traffic light controller, etc., etc. System diagram, inputs and outputs shown, inputs and outputs labeled, and tell me what a 0 and a 1 mean. Picture of the intersection, stick to WSE. Everybody did that lab 2, which is great. West, south, east for the inputs and for the outputs. Picture of the intersection, same labels as a system diagram. Truth table. Truth table should still have 3 inputs and 6 outputs. Do not simplify this, right? You can save yourself a lot of time by just saying, the red west is just the opposite of the green west. So I'm just going to do a 1 for green, 0 for red. Do not do that. You'll lose like half the points. All right. 3 inputs, 6 outputs. All right. Unminimized sum of products equation. This is the second half of today's lecture. We're going to talk about SOPs, POSs. Unminimized. Do not simplify them. All right. If you simplify them and come down to a minimum equation, you lose a chunk of points. All right. Once you have those unminimized equations, sketch a circuit diagram. So what do I mean by that? Use logic symbols, not pictures of chips, right? But use plain old logic symbols, the half moon for the AND gate, the curved thing for the OR gate, the triangle for the inverter, and so on. But for here, you do not need to include the switches. You do not need the LEDs, the pin numbers, the part numbers, the component ID blocks, and so on. All right, so you don't have to do all the things at this stage that you did for experiment 6. Right, so I'm giving you less work to do here. But I want something with logic symbols. So I want something like this. Here's my Western car input, and it goes into here, and here's my Eastern input, and it goes through an inverter, and this comes out, and it goes through an inverter, and this goes to an LED, and a resistor and ground, and this is, red, south. And this and this and this have to be in my system diagram. They have to be in my equations. They have to be in my truth table, and so on. And then maybe west goes into an inverter up here, and maybe east comes up here, and maybe those go through an OR gate, and this goes somewhere else, and so on and so forth, right? And unminimized equations, you're going to have a lot of gates in your circuit diagram. So you really want to do this on a whiteboard or pencil and paper or something like that a few times and figure out how you're going to lay it down, right? And we've talked about a way that you can have your inputs running like this, and you can tap into these and have your gates over here, and so on. Think about doing something like that. But make sure that this is something that it's pretty easy to look at and follow the connections. Don't make a spaghetti ball mess of wires, right? So you're going to have to redraw it a few times. So figure out what it looks like before you start writing the version of it that you're going to put into your lab report. All right, this is going to be a big circuit. Make sure whatever logic symbols you use are parts that are available in tinkercad. If you need to do an AND of 5 inputs and there's not a 5-input AND gate available in tinkercad, you can't use that. You got to break it into, say, a 4-input and a 2-input or something. All right, this is for SOP equations. Do the same thing for product of sum equations. All the way up to and including a circuit diagram. But again, you don't need switches, LEDs, pin numbers, part numbers, all that kind of stuff. Alright, so now you got 2 big, long, horrifying pictures. And they're not as bad as experiment 6. You didn't have to figure out which pins you were going to use and so on and so forth. But you can see 2 big mishmashes of logic gates and wires. Choose which one you want to actually build. And this is fairly subjective. Most people end up choosing sum of products. But whichever one feels right to you. But I want you to see both circuits that you've come up with based on sum of products and product of sums. See how they look similar, how they look different. Alright, compare the above 2 sets of equations and designs. Decide which one to use. Explain your thinking and why you chose one versus the other. And then, and only then, you get to minimize your equations. So we're going to use K-maps, which we're talking about today and Wednesday. Use K-maps, show all your work, come up with your simplified equations, and then you do the experiment 6 style complete wiring diagram. So this is where you have a component ID block in the upper right, a project ID block in the lower right, logic symbols, part IDs, pin numbers on all of the inputs and outputs of each and every gate, switches, LEDs, resistors, everything labeled, everything matching your system diagram and equations. Alright, and again in here, Tinkercad screenshots are great for showing your observations, for sharing those, as long as you describe what you're observing as well, but they do not take the place of a circuit diagram or a schematic diagram. Right? Anytime you're asked to make a circuit diagram in your lab, at the very least, you need to have, something with logic gate symbols, something that, an engineer can look at and immediately know, oh, there's an inverter, there's an AND gate, there's an OR gate, and so on. And in some cases, you've got to have all this other information. So you only need this for your final circuit implementation. And then after you come up with that, then you're going to actually implement that in tinkercad. Right? Minimize, implement, and test your recommended design from the previous parts using tinkercad. And what do you put in your test? Right? I tested it and it worked. Not sufficient. Because how is somebody else going to reproduce what you did? So how are you going to test this? Well, you've got 3 switches, you've got 8 combinations. And they represent different situations. So put your switches in a configuration which means there are no cars present. And what should your lights do? Well, it's up to you. Maybe one light will be green, maybe they'll all be red. Did you observe that? Well, make a note of it. Now I had a car arrive to the south. Put my switches in this configuration. And now the south green light was on and all the other red lights were on and the other green lights were off. And that's what it should do. Okay, that's a good observation. Now while leaving the car to the south, I brought a car to the east by flipping, this switch to the on position or the off position, and in this case, here's what the LEDs did, right? So you've got to explain exactly what you did to test your circuit so that, again, if somebody else tries to reproduce your work, they build your circuit, they can go through the same set of tests and say, oh, I put the switches in the same configuration, but when I did that, a unicorn popped out of the protoboard and ran away. So something different happened here. Why is this different? Is it because I was in a different hemisphere? Or is it because I used a 74LSO4 instead of a 74HCO4? Right? So you've got to have enough detail so that somebody else can go through the same steps you did and say, yeah, exactly the same thing happened, or hey, something different happened. And if something different happened, hey, you're doing science. You're making a discovery. And somewhere down the road, a theory is going to be modified or expanded or maybe tossed out. Right? So that's what's going on here. All right. And so lab 3 is a due date of the 29th. So you've got some time, right? So this is a week from Friday. I'm not doing that just to be nice, right? I'm doing that because all of this is going to take a huge amount of time. This step 3, this could be 2 or 3 pages worth of circuit diagram. You're not going to be able to sketch that out, while you're standing in line at the grocery store and you've got the back of a receipt to write on, right? This is going to be huge. This is going to be huge. This is going to be relatively small. But these steps here, 3 and 4, big circuits. And you're seriously going to have to probably redraw them 3 or 4 times to get them into a shape that you can actually like make look, like an understandable circuit and put into your lab. All of this works a whole lot better by hand than using tools on a computer, by the way. At least my opinion and experience of most students I've seen. Drawing this neatly by hand, good sharp pencil, nice clean paper, maybe a straight edge, will get you designing a lot quicker. And it makes it pretty easy to make changes because you can erase. Alright, questions about lab 3?
What did the abstract and midterms mean on the first page? Or are they pages before this?
Minterms and max terms. We will talk about that after break. So we're going to spend the next half hour just talking about sum of products and probably not product of sum. So we'll start breaking this down in detail.
So to go from truth table to circuit design, you have to do the equations first, right?
Yeah, you need the equations first, and then
Okay, got it.
from there you can go to circuit. So it'll usually look like this.
When you're doing the equations, I noticed that even from the chapter J homework, there's sometimes it's like not all of the inputs are there. Like it's x plus z, and there's no y.
Mm-hmm.
But does that mean it doesn't matter if what y is? It could be either 1 or 0.
Exactly. Yep.
Okay, got it.
And we'll see how to get those simplified equations.
Awesome. Okay.
Cool. All right, so we're gonna do like a 4-minute break, and then we'll come back and we'll start digging into how to write equations from truth tables. So let's come back at 9:23. Sharpen my pencil.
Oh yeah. Good morning.
Did I screw it?
A little bit, that's okay.
Alright, welcome back. So I have been recording this lecture, I just didn't have my little recording meter up here, but This should all be recorded and posted later. Someone asked, are you using a terminal to control your recording software? Pretty much. I'm using the terminal for pretty much everything, including the cameras. Alright, so our whole question is writing equations from truth tables. So, truth tables. To equations. And so here's a typical layout for a truth table. So I'm gonna pick on circuits containing 3 inputs, but this is going to be the same process for 4 inputs or 2 inputs or whatever. But let's just imagine we have, you know, some set of inputs A, B, C, and we have some output F, which we can think of F of A, B, C. So we can write it kind of like a function, right? And I don't know what our outputs are going to be. Let's go back to the cookie jar. So we're going to do, like, you know, something like this. So let's suppose that's the set of outputs that we want. And so we learn a way to write an equation for F by doing the following procedure. We look for everywhere where we have a 1. And wherever we have a 1 in our output, we write down a certain combination of A, B, C, A bar, B bar, C bar. And so in this case, we would say F equals, well, there's a 1 right here. If we see a 0 for the A input, we write A with a bar on top. If there's a 1 for the B input, we write B without a bar. There's a 0 for the C input, we write C with a bar. And then we have another place where we want our output to be 1, so we're going to say OR. And here A and B have 1s, so we write A, B. And C has a 0, so we write C bar. And there's another place where our output should be 1, so we'll say OR. And here A, B, and C are all 1, so this is just A, B, C. So there's an equation corresponding to this truth table. And it takes no real effort other than, you know, everywhere that we find a 1, writing down the correct term corresponding to this set of inputs. And if someone comes with another truth table and they call this variable W, but it's got the same 0s and 1s in the output, and I go through the same process, I'm going to get the same result. W equals A bar B C bar, or A B C bar, or ABC. So this is really just kind of a dance between, you know, this column of 1s and 0s and these terms that I'm writing down here. And if this becomes a 1 suddenly, right, I would just OR another term, and that term I would OR in this case would be A, B bar, C bar. And so after you've done this a few thousand times, you start to notice patterns. And you start to think, hey, you know, I don't have to reinvent the wheel every time I have a new truth table. I'm going to make myself a little cheat sheet. And here's what I'm going to do. I'm going to just write down, regardless of what my truth table actually is, I'm going to write down a key I'm going to use. And my key is going to be the following. If I have a 1 here, I'm going to write down A bar, B bar, C bar. If I had a 1 right here, I would write down A bar, B bar, C. In here I would do an A bar, B, C bar, and here would be A bar, B, C. And so we can start to build up a table. And so let me do this on a different page and not worry about a particular function f. And let me just write down these expressions that I would write down as, you know, part of an equation. So A bar, B bar, C bar, A bar, B bar, C, A bar, B, C bar, A bar, B, C, and so on. And I recommend doing this many times because it'll make it easier to remember. But now I've got a little like cheat sheet. If someone hands me a truth table and I want a one like here, here, and here, well, it's just this, ORed with this, ORed with this. I'm done. So now this question of, you know, here's a truth table, show me an equation. Well, it'll take me about 5 seconds to write that equation now. If I want a truth table that has a 1 here, here, and here, what's the equation? A bar, B bar, C bar, or A bar, B bar, C, or A, B bar, C. I'm done. 5 seconds. Engineers are lazy. This is our nature. Well, it's not necessarily our personality. To me, I'm very lazy. It's part of why I like engineering, because engineering lets me be lazy. Engineering is about finding, you know, tips and tools and tricks and techniques that save me time and energy. So now if I want to write an equation for a truth table, I barely have to think. All I have to do is be able to find where the ones are in my truth table and write down the corresponding terms from here and put plus signs in between them. So this is a pretty useful little cheat sheet. And this column of product terms is particularly useful. So we give names to things that are useful. These things have names. These are called minterms. They are also product terms, or just products. Product is the same as anding, right? If this was algebra, this would look like A times B times C. And when you take Boolean variables, you know, if any of them are 0, then the and is 0. So they kind of look like products. So these product terms are called minterms. And using these minterms to write an equation, our equation becomes what? It's a sum of these minterms, which are products. So this is an SOP representation of an equation corresponding to a truth table. So in our homework or in our labs, and the homework, by the way, again, is due Friday, not Wednesday. So there's extra time on it. So when we talk about using sum of products or a minterms approach, this is all we're talking about. We're saying let's go ahead and write this as a bunch of these product terms, which are called minterms, being summed or ORed together. All right. So for an SOP, we write our function as a sum or an OR of minterms. And so on the homework questions, when you're asked to express something as a sum of products or in minterm representation, right, you should be writing something like this. It means we don't have parentheses, we don't have exclusive OR gates, we don't have NAND gates, we don't have NOR gates. We have a bunch of terms, each of which is a product or an and then we take all those terms and we OR them together. That gives us a sum of product representation. All right, think lazy, right? I have a truth table and I want, it to output a 1 here, here, and here. Well, all I have to do is I have to write down the minterms corresponding to each of those rows of my truth table, and I just OR them together. Well, if every engineer knows what these terms are, why should I bother writing them out? So we have abbreviations for these. We call this little M0, M1, M2, M3, M4, M5, M6, and M7. And now, instead of writing all of this stuff, I could say F equals M2 or M6 or M7. All right, this is called compact form. And one thing to be careful of, right? This is completely clear. My output will be 1 if A is 0, B is 1, and C is 0. But when I write this, how do I know that that's what M2 means? How do I know that A is 0, B is 1, and C is 0? Unless I know that my truth table inputs are ordered A, B, C. In other words, if I labeled these C, A, B, right, then this 1 would correspond to A is 1, B is 0, C is 0. So usually when we write compact form, you have to say something like FA, B, C equals M2 plus M6 plus M7. So that I know when I mean row 2, I'm talking about row 2 when my inputs are in this order. So yeah, for the lab, you're going to have as many ORed terms as you have ones in your truth table. And this is all for, a single output, but in lab 3 you have 6 outputs. So you're going to have 6 truth tables, and you're going to have an equation for each of those truth tables. So you'll have 6 equations total. And for each one, well, depending on how many ones you have, that'll be how many of these minterms you have that get ORed together. Alright, so this is a compact form. We can make it more compact by using a summation symbol like this. And when you see something like f of a, b, c equals summation 267, we understand that to mean this should be equal to 1 if our inputs match minterm 2, 6, or 7, meaning this combination, or that combination. So this is a super duper shorthand way of writing that. And it's based on this idea that we can standardize, what these minterms are, and we can just use those to represent these more complex product terms. So your homework has a lot of questions related to this. So for example, write the corresponding compact minterms for each of the functions fa, fb, and fc. So here's, 3 inputs, a, b, c. Here's one output, fa. Well, let's go to the solved one, right? Here's one output, f1. Well, this should be a 1 when we're in this input combination. I can't point in PDFs. this input combination, or this one, or this one, or this one. Well, in compact minterm form, right, this is saying that minterm 3, minterm 4, minterm 5, or minterm 7. So we could write F1 equals sum 3, 4, 5, 7. And that's the compact representation of F1. F4 should be a 1 when our input corresponds to rows 2, 3, 4, 5, or 6. So F4 is just sum of 2, 3, 4, 5, 6. Right? And this is just a very succinct way of writing in this case. F4 equals A bar B C bar, or A bar B C, or A B bar C bar, or A B bar C, or A B C bar. So it's this direct translation we can make between these terms and these little abbreviations, or just writing down, you know, which row of the truth table should have a 1.
I have a question.
Sure, go for it.
Which way do you want us to write it? With the M's, with the just the numbers, or with the A naughts, B naughts, and whatnot?
So if it asks you for just, you know, a sum of products, or sometimes it'll be called canonical form. If it asks you for a sum of products and it does not say compact form, write it like this. But if it says compact form, you can write it like this, or you can write it like that. Now, if you're trying to build a circuit, you probably want it in canonical form so that you can see, you know, exactly what the inputs are, which ones are inverted, how many inputs you need on your AND gates, and so on and so forth. But some of the homework questions will say, you know, write in compact form. Some will not say that. If it doesn't say use compact form, write it out as, you know, a bunch of product terms with ors in between. And that's sometimes referred to as canonical form, but it's also just the form that's not compact. All right, let me talk a little bit about product of sums, but then I want to talk about simplifying equations that are written as sums of products, and then we'll come back and talk more about product of sums. But let me introduce product of sums first, and then we'll talk about we'll start talking about minimizing. So let's look at another equation, another truth table. And let's imagine some output function f of ABC. And let's suppose this is what our truth table looks like. So if I were to write this as a sum of products, I would have 6 product terms, M0, M1, M2, M4, M6, and M7, all ORed together. Each of those product terms is a 3-input AND gate, and since I have 6 of these, I need those 6 outputs to go into a 6-input OR gate. So there's a lot of logic involved in writing this as a sum of products. Sum of products, we're basically trying to write something that identifies when the output should be a 1. But there's a dual way that we can write our equation for f using what's called a product of sums. And a product of sums we get by looking for the terms which should be a 0. And in this case, we have only 2 terms which should be a 0. And I'm going to do something parallel but different from what we did for sum of products. I'm going to write a sum term instead of a product term. So I'm going to write a bunch of things ANDed together, and it's going to be a combination of A, B, C, A bar, B bar, C bar. But in this case, if I have a 0 in my input, I'm just going to write the variable. If I have a 1, I'm going to write the variable with a bar on top. And I'm going to put pluses in between them. And so for this 0, I see an A, I'm going to write A bar. I see a 0, I'm going to write B. I see a 1, I'm going to write C bar. And now I'm going to take these and I'm going to take the product of those, and I'm going to say f of A, B, C equals A or B bar or C bar, ANDed with A bar or B or C bar. And this is going to give me the exact same truth table. So we're back to KVL, KCL. We're back to all these things that we encounter in math and science and philosophy, where things come in duals. And this is a different version of a sum of products, but it's called a product of sums. And for most people, sum of products makes more sense than product of sums. This feels backwards in some way, but let me try to point you towards what's going on here. What we're doing is we are writing an expression which will be 0 in this case and in this case. And we're ANDing these expressions together. So if this expression is 0, our output will be 0. If this expression is 0, our output will be 0. In any other case, if these are both 1, our output will be 1. So here we're identifying where we want our output to be 0, and we're writing an expression which will be false in exactly that case. So why is this false in this row? Because in this row, A is a 0, B is a 1, C is a 1. Well, this will be false, this will be false, this will be false. The OR will be false. But if we're not in this row, either A is a 1, which makes this true, or B is a 0, which makes this true, or C is a 0, which makes this true. So this term is 0 exactly when we're in this row of the truth table. With sum of products, this was 1 exactly when we were in this row of the truth table. Here we're writing an expression which is 0 in this row of the truth table. And by multiplying those, by ANDing those expressions together, this final expression f will be 0 if we're in this row or this row. At some level, this is just De Morgan stepping in and rewriting our work for us. And we would end up with a product of sums instead of a sum of products. So we can define what are called max terms. And max terms, we just use the slightly different rule. If we have a 0, we write the variable without a bar. And we OR all of our variables together. So here we put a bar over the C because the C input is a 1. And so we get another cheat table. Which looks like this. And these are called the max terms. And these are sums. And if we have any truth table, and we want to write the equation as a product of sums, all we do is find each point in the truth table where our output is a 0, write down the corresponding max term, and then we multiply those together. So for example, if I had a function f, and so here was our original function, and I want to write a product of sums, I can do the following. I can write the max terms everywhere that I have a 0. So this will be A or B or C, ANDed with A or B or C bar, ANDed with this third one, A or B bar or C, ANDed with the 5th and 6th rows, so A bar or B or C, ANDed with A bar or B or C bar. And that's a product of sums equation for f. So sum of products look like this, product of sums looks like that.
I have a question.
Yeah.
Does the ends here and 1 and 2 apply to max terms as well?
So for max terms, yes, but we use an uppercase M.
Okay.
So all of this I could write more succinctly as a product of max terms. So max terms 0 times 1 times 3 times 4 times 5. And just like we can use a summation to get rid of these plus signs, we can use a product sign, which is an uppercase pi. And so these are compact forms. And this is a canonical form. So in this representation, this doesn't really look all that much more complex than this. It's a little more complex because there were more zeros than there were ones. But, you know, it's product of 0, 1, 3, 4, 5, or sum of 2, 6, 7. But when we write out the actual equations, this kind of looks a lot more complex than that. In some way, it's really not, but it kind of looks like it. And so we have two completely different but dual ways of writing an equation from a truth table. One is a product of sums or a product of minterms. The other is a sum of products or a sum of max terms, right? Sorry, a product of sums or a product of max terms. So this is, you know, a bunch of sums, right? A bunch of OR expressions, and we're taking their product or their AND, so that's a product of sums. Whereas this was a bunch of products and we summed them together, so it's a sum of products. And the homework questions will take you through a whole batch of exercises of writing equations in one form or the other, or converting from one form to the other, or thinking about how the two forms are related to each other. And so the homework's a lot of work. Like I say, you have until Friday for that one instead of Wednesday. And then the lab will have you doing this also. So what we have not gone over, which is simplification using K-maps, and we'll start Wednesday by talking about that after any questions. But this should get you through most of homework 2. The questions that ask about simplifying, we'll have to go through K-maps on Wednesday. But other than those, and I think there's only one, possibly 2 of those at the end. Other than those, this should get you on the air. So two details. Check Canvas for homework details, because there's usually some additional information, like don't do this question, or for this question only do this thing, or possibly do something in addition to what's written. So make sure you always check the Canvas entry for the homework assignment for more specific instructions. And then if you can, get started on this as soon as possible if you haven't already started it. Come by office hours tomorrow, or bring questions to class Wednesday. And Wednesday, like I say, we'll start with questions, and then we'll jump into simplification with K-maps, and then we'll dig deeper into more examples and analysis of max terms and min terms. But this will basically be what we're doing for the rest of the week. All right, that's all I got. Hope everybody has a great day, and I will see you all next time.
Awesome. Have a good one.
Thanks, you too.